Hi, welcome to another session of lecture on AEW 1 to 5 Business Statistics. Last week I covered the chapter 7 which included sampling distribution, and this week in chapter 8 we will move on to another topic called confidence interval and estimation. In this chapter what you will be learning is how to construct and interpret confidence interval estimates for the mean and also the proportion. You will also determine the sample size necessary to develop a confidence interval for the mean or proportion. These are the chapter outlines, and content of this chapter will include confidence interval for the population mean. This will cover two parts, when population standard deviation is known and also when population standard deviation is unknown. Next, we'll also look at confidence interval for the population proportion, which is denoted by pi. And the last part we will look at determining the required sample sizes for estimating mean and also the proportion. So in this chapter called estimate, we will learn about two estimates. One of them is called point estimate. The other one is called the interval estimate. A point estimate is a single number, whereas a confidence interval provides additional information about the variability of the estimate. So the confidence interval will have what we call as a lower limit and also an upper limit. So the width is called the confidence interval. For point estimates, we have two estimates that we can do. One is for the mean, the other one is for the proportion. Mean is denoted by mu and the proportion is denoted by pi. The sample statistics for mean is denoted by x bar, and the sample statistics for proportion is denoted by the p. What are confidence interval estimates? An interval gives a range of values. It takes into consideration variation in sample statistics from sample to sample. Based on observation from one sample, we will calculate a point estimate, and the confidence interval will give us information about how close the unknown population parameters are. The confidence interval is normally stated in terms of level of confidence. We normally look at two levels of confidence, which are 95% confidence and 99% confidence. We will never be 100% confident. So we'll look at an example of the serial field example. The population mu is 368 with a standard deviation of 15. If you take a sample of n equals to 25, you know that the 95% confidence interval for the sample mean of size 25 will include 368 plus minus 1.96 times your standard deviation divided by a square root of your n. So 95% of the means will be between 362.12 and 373.88. Okay. When you don't know the mu, when we don't know the mu value, we can use the x bar to estimate the mu. So if the x bar is 362.3, the interval estimate will be the x bar plus minus your z times your standard deviation divided by square root of n. So now the 95% confidence interval is 356.42 and 368.18. Okay, this is only one sample. But what about the intervals from other possible samples of size 25? This is what we will be looking at next. Now we have taken 5 different samples: sample 1, sample 2, sample 3, sample 4, and sample 5. The x bar we already know from the previous slide, it was 368. And for sample 1, the X bar was calculated at 362. Second sample was 369. Third sample at 360. Fourth one is 362. And the fifth one is 373. The X bar will be in some samples higher than the mean values. In some samples it will be lower than the mean values. So next we calculate the lower limit and the upper limit, and what we find is here the first sample we have a 356 to 368, and the mu value of 368 is still within the lower and the upper limit. For the second sample also is within, but for the third sample if you see the lower limit is 354 and the upper limit is 365, whereas the mu value is actually 368, so it's actually outside this limit, so it doesn't contain the mu value. Sample 4 and sample 5 we still have, so that is why in some samples the mean value will be higher than the X bar will be higher than mu value. In some means it will be lower than the mu values. So in practice, you will not only take one sample, and in practice you do not know mu value, so you do not know if the interval actually contains mu. However, you do know that 95% of the intervals formed in this manner will contain your mu value. Thus, based on one sample you actually selected, you can be 95% confident your interval will contain the mu values. This is what we call as 95% confidence interval. So the estimation process works like this. We have a population here where the mean is mu and is unknown. We will take a smaller sample from this population. This is the sample which is smaller, and then we will estimate the X bar. So by doing this, we can say that 95%, we are confident 95% that the mu value will be between 40 and 60. That is what we call as the estimation process. The general formula to calculate all confidence interval is given here, which is the point estimate plus minus critical value times standard error. What are critical values? Critical values are the table values that you get. It can be sometimes Z, it can also be a T, and this follows the normal distribution or the T table distribution. So the point estimate is the sample statistics estimating the population parameter of estimate. The critical value is from the table, and the standard error is the standard deviation divided by square root of n. The confidence level, which is denoted by 1 minus alpha here, is how confident are we that the interval will contain the unknown population parameter that we are estimating. This percentage will be less than 100%, and suppose confidence level is 95%, also written as 1 minus alpha equals to 0.95. So your alpha is actually 5%. So 1 minus 5%, you get 95%. So the confidence level is 95%. So a relative frequency interpretation is 95% of all confidence interval that can be constructed will contain the unknown true parameter. Only 5% of the time the X bar that we calculate will be outside the true parameter. So when we calculate confidence interval, there are two formulas that we can use for population mean. One is when the mu is when the sigma is known, and the second one is when the sigma is unknown. We will first look at the formula to calculate confidence interval when the sigma is known. To calculate confidence interval for mu, sigma known, these are some of the assumptions that you need to understand. Number one is population standard deviation, which is sigma, is known. Population is normally distributed, and if population is not normal, we can use large samples and greater than 30. So the confidence interval estimate formula is given here. X bar plus minus Z alpha divided by 2. This is your table value. So if it's 5%, then the Z value will be 1.96. If it's 1%, the table value will be 2.576. And times your sigma divided by square root of n. That's how we use this formula to calculate confidence interval. How do you find the critical value of Z alpha divided by 2 from the table? So since our confidence here, the shaded region is 95%, the tail will have 0.025 and this part will be 0.025, which is 2.5% here, 2.5% here. So the critical value, which is this number here, for 5% confidence, 5% alpha value is negative 1.96 and positive 1.96. So the common levels of confidence that is used in many statistics books are, these are some of them, 80%, 90%, 95%, 98%, 99%, and whatever. But most of the time in our classes we'll be using 90%, 95%, and 99%. So for 90%, the table value is 1.645. For 95% is plus minus 1.96. And for 99% is plus minus 2.58 or 2.576 from the table. So when we calculate intervals and level of confidence for separate samples, we have different samples. Some of the samples will be like this in sample 1 here, sample 2, sample 3, sample 4, sample 5, sample 6, and 7 here. Okay. This sample particularly is outside the region, whereas the rest of the samples are actually within the 1 minus alpha, which is 95% confidence. So next we'll look at an example. In this example, we have a sample of 11 circuits from large normal population. It has a mean resistance of 2.20 ohms. We know from past testing that the population standard deviation is 0.35 ohms. Determine a 95% confidence interval for the two mean resistance of the population. So to solve this kind of questions, what you first need to do is, we will first write the formula, which is X bar plus minus Z alpha divided by 2 times sigma divided by square root of n. So the X bar is given here 2.20. The Z value is, for 95% confidence, we saw in the table before, 1.96. The standard deviation is 0.35 and the n is 11. So here we have a 2.20 plus minus 0.2068. So the lower limit will be 2.20 minus 2.20 minus 0.2068, which will be 1.9932, and the upper limit will be 2.20 plus 0.2068, which is this part here. So what we can conclude here is, we are 95% confident that the true mean resistance is between 1.9932 and 2.4068 ohms. Okay. Next, I will walk you through an exercise, which is exercise 1. This is an exercise from your page 315 of your textbook, exercise 8.1. In this exercise, the question says, if X bar equals to 66, sigma equals to 6, n equals to 64, construct a 99% confidence interval, estimate for the population mu. So to answer this, we will first write the formula, and for 99% confidence, the Z value is 2.58 or 2.576. So the formula is X bar plus minus Z alpha divided by 2, which is 2.58, times sigma divided by square root of n. So your x bar is 66, sigma is 6, and your z value is 2.58, and your sample size is 64. So we get 66 plus minus 1.935. So the answer will be 64.065, which is called the lower limit, and 67.935, which is the upper limit.